Okay, today we will present target-aware vectorization for irregular loop or instruction patterns. We are from Bison compiler team from the Huawei compiler labs. So first is about the SIMD and vectorizations. Parallel computing is the key to CPU performance in post-Moore's law era. We are familiar with three different kinds of parallel. First one is TOP, the thread level parallel, and another is the instruction level parallel, and the last one is the data level parallel. Today we wanna focus on the DOP, the single instruction multi data. Most common modern CPU will support SIMD operations, and maybe we have some ways to support the SIMD code generations. The first way is we just use assembler, or we use the compiler intrinsic to write the code. And another way, we will depend on the compiler automatic vectorizations. So it must follow two assumptions. One is that the SIMD instruction must perform the same operations across all lines and without the cross-line operations, but we will encounter some irregular or complicated SIMD instructions. Maybe break the above two assumptions. The first, like the instruction complex, compact, dot product, or the HISTCNT. So how can we handle them? So we can see the SIMD path pipelines. The most important one is the loop vectorize. I just mentioned. So it will have for the vectorized path, it will generate most of the vector instructions by the loop vectorized path, the SLP vector path, or the vector combine path. At the early stage of the path pipeline, we have a loop idiom, named the loop idiom recognition. So it will do some pattern match to match some idiom loops. Also, we have the AX64 and the hexagon. We have the target dependent idiom path. Also, we have the iselect close, just close to the back end. We have the iselect path and the instruction selection path. So the key question is that should this path of the optimizations be target aware? So we just look at the list of the IFCs and the patches. We can see that most of the instructions or the patterns, they are the target dependent. And even for the loop vectorization, we should use the TTI interface to check whether the target can support the target dependent instructions. Let's look into the details. The first is the loop idiom. I think I already mentioned it in the previous page, so I skipped it. But we can see the pros and the cons. For the advantages, we can see the loop idiom path because it's early enough in the pipelines. So it will not be affected by the other, by the later optimizations, and it can be target specific or it can be target independent. So it will be flexible and easy to implement. But for the disadvantages, because matching the idiom code was very hard and pretty fragile, and the IR may be changed by the path before it, like the inst-combine. And another disadvantage is because it's too early in the pipeline, so may lose some optimizations. So maybe the loop idiom path may complain that, oh, it's so hard for me because I'm early enough in the pipeline, and I'm so smart, but I just look like a fool because I'm too early in the pipelines. So what should I do? So we just seek the help for the loop vectorized path. So luckily we have the Vplan and we have some patterns, loop patterns, just like the left side some box with different colors. Obviously, current Vplan framework cannot handle it. So, but I think we can add some new recipes. So Mindong can introduce the details.
Okay, next I will give some examples of how we enabling SV instructions in LLVM and the considerations behind. Okay, the first example is SV's compact instruction, and it shuffles the active element to the right side of the destination vector with the left element set with zeros. And this is not a rare example, and 2 hours before there is a related presentation from TEJS, and this is a proof. Currently, even though there is already a middle end intrinsic for this pattern, LLVM loop vectorized parts cannot generate the vectorized code for this. And you can see there is unidentified file from the debug information. So what does it mean when you got an unidentified file? So currently only 3 types of files are recognized: inductions, reductions, fixed order recurrencies, and for the compact pattern, this cannot be categorized into any of the existing pattern. So something new needs to be added to the vectorizer framework. So what do we need to do? Here's the main list of the things we need to add to the vector framework. Okay, first a new descriptor for the compact node, and also some new recipes added to the Vplan, and of course the target specific lowering, because you want to get the exact the compact instruction rather than being expanded into something else. Yeah, and yeah, for the construction of the new descriptor is also the process of finding the related instructions of the compact instruction chain. Okay, first the compact header file, and also the compare instruction, then the add instruction that actually updates the value of file, and the get element pointer to compute the address, the store, which will turn into the compact instruction, and also a latch file. Also, now we get all the instructions to compose the descriptor. Now we need some recipes to determine how these instructions will be vectorized finally. And yeah, we added 3 new types of recipes for this pattern: compact file recipe and a CNTP recipe, which counts the active elements in a vectorized iteration, and also a compact recipe. Okay, and you can see the compact recipe turn into a mask compressed store, with then lowered into a compact instruction with additional store, which is not depicted in the slide. And the CNTP recipe will turn into a vector reduce add to count the element number. And there is an early POC version of this job, and those slightly different from these slides. And as you may already wonder, this might not as general as possible, and yeah, we can tweak the code a little bit, and without changing the control flow. You can see the following 2 patterns cannot be vectorized by the current vectorizer. Yeah, partly because the control flow is eliminated by the if conversion, and the loop vectorizer treat these 3 patterns differently. And maybe in the future, we may need to find a more uniform way to vectorize all these patterns. And for the TSV's case, we have internal version to use C++ to vectorize the code, and later we will contribute it to the upstream community. And there are also some simple cases. For example, there is a native instruction for load exponent math function, which in SV is f-scale. And this is a simple one because you can, there's already an intrinsic inside the LLVM middle end, and you can directly tell the vector utils that there is a mapping of the load exponent math function to the middle end intrinsic, and that is quite simple. And this case is special in that you can also make use of the f-scale instruction to speed up the code, even though the loop cannot be vectorized. in the end. Thanks to the fact that the lowest bits of the SV registers are overlapped with the CMD registers, and you can use the first lane of it with the help of the instruction. Okay, there is also some more ongoing work. I think I'm already time out. And HISTCNT is instruction for histogram computation, and it can also be used to do some conflict detection as part of runtime check to vectorize more patterns. And there is already an RFC raised by our team to support this, and we'd like to contribute our ideas there. Okay, thanks. That's all from today's topic. Thank you.